Welcome to lecture series on CFD part 2. This is lecture 23 on finite volume methods for polyhedral grids. Most commercial and public CFD codes are based on finite volume methods and can use grids made of arbitrary polyhedral control volumes. We describe in this lecture the data structure for such grids, how a polyhedral control volume is defined, and how are surface vectors, phase, and cell centroids computed. The next topics are approximations of surface integrals for convection and diffusion fluxes and interpolation methods to compute variable values at phase centers. Gradients of variables are used in many terms, and we describe two widely used methods for computing gradients at cell centers. Approximation of volume integrals is the next topic, followed by the treatment of non-conformal grid interfaces. Finally, the derivation of a pressure correction equation for polyhedral control volumes is described. Finite volume method starts with a conservation equation in integral form. We use the conservation equation for a generic scalar variable to describe methods that are common to all equations. This equation has four main parts: the rate of change term, the convection term, the diffusion term, and the source of sink term. The solution domain is discretized into a finite number of contiguous control volumes, which can be of any arbitrary polyhedral shape, as shown in this plot. The integral conservation equation is applied to each control volume, and all terms need to be approximated using geometric data, fluid properties, and variable values at cell centroids, which are the discrete points at which the solution is computed. Three levels of approximation are used: numerical integration, that is, approximation of surface, volume, and time integrals; interpolation, that is, computing variable values at locations other than cell centroid; and numerical differentiation, that is, approximation of gradients. Note that gradients of variables are needed both at cell centers and at phase centers. Let us first see which data is needed to describe an unstructured grid made of arbitrary polyhedral control volumes. The main entities of such grids are vertices, faces, and cells. First, the vertex list must be defined. Each vertex is assigned a unique number and is defined by its three coordinates x, y, and z. Next, a list of all faces is required. One distinguishes between internal cell faces, which are common to two control volumes, and boundary cell faces, which are attached to a single control volume. Boundary faces are usually grouped for each solution domain boundary. The face list contains the following information: a unique face number, an ordered list of vertices defining the face. For example, this face is defined by these five vertices: V1, V2, V3, V4, and V5. Surface vector components, coordinates of phase centroid, indexes of the cells on either side of the face, matrix coefficients multiplying variable values at cells on either side. For example, for the phase common to these two control volumes, we store the coefficient from the algebraic equation for this control volume, which multiplies the variable value at this neighbor cell, and the coefficient from the algebraic equation for this control volume, which multiplies the variable value at this neighbor cell. Finally, a list of cells is needed. It contains the following information: a unique cell number, a list of faces enclosing the cell, number of faces followed by face IDs, cell volume, coordinates of the cell centroid, variable values and fluid properties at cell centroid, and matrix coefficient from the main diagonal and the source term, the right-hand side. A face is bounded by straight edges, even though it may not be planar. This is important because face projections to Cartesian coordinate planes are unique if the face is bounded by straight line segments, irrespective of its warpage. These projections are the components of the surface vector, which thus can be exactly computed. Even though the surface vector is exact, the position of face centroid is not uniquely defined for non-planar faces. To make the face and cell centroids unique, face triangulation is usually used. It also helps to compute the cell volume. Face triangulation can be performed in different ways. For the blue face in this figure, we could connect vertex V1 with vertices V3 and V4 and thus create 3 triangles. However, this approach can lead to problems if the face is defined by a non-convex polygon. A safer approach, which creates more triangles, is to define an auxiliary hub point H at each face. Its coordinates can be defined as the average coordinates of all vertices defining the face, as given by this expression. Here, RVI represents the ith vertex on face K in the list of vertices defining the face. The cell face is subdivided into NKV triangles by connecting each vertex with the hub H. Because triangles are planar, their surface vectors and centroids are easily computed. For example, the surface vector for nth triangle is half of the vector product of two vectors connecting the hub point with two vertices, as shown in this expression. The surface vector for the whole face equals the sum of surface vectors for all triangles. The coordinates of the centroid of each triangle M, RKM, are defined as 1/3 of the sum of vertex coordinates. The position vector of the centroid is given by this expression. The coordinates of face centroid, which are stored for use in the discretization process, are obtained by weighting the coordinates of centroids of each triangle with its area, as shown by this expression. To compute cell volume, another auxiliary hub point H is needed. The coordinates of this point can be defined as the average coordinates of all cell vertices, but any other position within the cell would also work. One can now connect vertices of each triangle in each face with the hub point H, thus creating a tetrahedron whose volume can be easily computed as 1/3 of the scalar product of two vectors: the surface vector of the triangle in the cell face and the vector connecting the hub H with the cell hub H. The cell volume can now be computed by summing volumes of all above defined tetrahedra attached to triangles in all cell faces. Here, NPF is the number of faces enclosing the control volume around node P, and NKV is the number of triangles in face K. The coordinates of cell centroid P can be computed by weighting the coordinates of each tetrahedron with its volume, as shown in this expression. Here, the coordinates of tetrahedron centroids are defined as the average coordinates of their vertices. The control volumes defined in this way are not overlapping. The sum of volumes of all cells equals the volume of the whole solution domain, bounded by boundary faces triangulated as shown in this figure. In lecture 7 and 8, various methods for approximation of surface integrals were described. Not all are applicable to polyhedral control volumes, whose faces can be polygons with any number of edges greater than 3. Midpoint rule is the simplest second-order approximation of surface integrals that is applicable to any polygonal face. Surface integral of any quantity is approximated as the product of that quantity at face centroid times face area. The shape of the polygon is irrelevant. To compute the mass flux for a cell face, we take a dot product of velocity vector and surface vector, which is equivalent to multiplying the velocity component in the direction of face normal to the face area and multiply the result by the density at face centroid. The velocity component normal to cell face is obtained by taking a dot product of velocity vector and a unit normal vector n. The surface vector is expressed by its three Cartesian components, or the face area and the unit normal vector. The convection flux of a generic variable phi is approximated as the product of face mass flux and the variable value at the face centroid. The mass flux is taken from the previous iteration, which corresponds to the Picard iteration scheme. Variable values at phase centroid must be expressed via nodal values at cell centers by means of a suitable interpolation. There are many options for computing variable values at the phase centroid. Linear interpolation between nodes P and Nk leads to the value at location K prime, which is not the phase centroid. Using this value as an approximation for the value at phase center reduces the order of approximation to first. The second order can be obtained by applying a correction based on Taylor series expansion. We add to the value at K prime the scalar product of the gradient at K prime with the distance vector connecting K prime with K. Gradient vectors are usually computed at cell centers anyway, and the value at K prime can be obtained by linear interpolation as in this expression. Another option to compute the variable value at phase center K is extrapolation from the upstream side. This is the default practice in Simpson-Stasis M+, and is called second-order upwind scheme. The underlying part is treated as a deferred correction, that is, evaluated using variable values from previous iteration. Here is an example which illustrates the importance of using second-order approximations. We compute the invested stagnation point flow using the grid shown in the left figure. The bottom left corner is the stagnation point, where the velocity equals 0 and the pressure has its maximum. We know the exact solution for this problem. Pressure contours are circles centered around the stagnation point. The middle plot shows pressure contours computed when using linearly interpolated values from neighbor cell centers as an approximation for the phase center value. For phases along the diagonal, the locations K prime and K do not coincide, because grid lines change their direction by 90 degrees. At all other phases, the two locations coincide. The error introduced at the phases lying in the diagonal is reflected in pressure contours by disturbances. When we apply correction to the interpolated value as described in the previous slide and shown in this expression, we obtain smooth pressure contours across the diagonal. Another option for computing cell phase values is extrapolation from both sides and applying weighting according to distance. This is the second order upwind approximation, and this is the second order downwind approximation, assuming that the flow is from P to Nk, or the other way around. Upon weighting with distance, we obtain what is equivalent to a central difference approximation or corrected linear interpolation. Yet another option is to use auxiliary points at phase normal. We take a dot product of vectors connected P to phase center and phase center to neighbor cell center Nk, and define the smaller of the two distances as A. In this figure, A is the distance from P prime to K. We set the other auxiliary point on the normal at the distance A from phase on the other side of the cell phase. Variable values at these auxiliary points can be computed using cell center values and gradients times distance vector from cell center to the auxiliary points, as shown by these two expressions. The phase value is now obtained as the average of values at the two auxiliary points because they are at equal distance from the phase. Let us see how one can approximate diffusion fluxes on polyhedral grids. First, apply midpoint rule for surface integral in the expression for diffusion flux. The scalar product of gradient vector and the unit normal vector represents the derivative of phi in the direction of phase normal. We therefore need to interpolate the diffusion coefficient to phase center and to approximate the derivative of phi with respect to n at phase center. The simplest second order approximation is the central difference, using variable values at the two auxiliary points on phase normal defined in the preceding slide. The value at this point minus the value at this point divided by distance. This is a second order approximation because the points are equidistantly spaced with respect to phase center. Approximation of values at these 2 points are also second order. In section 972 of the book, another approximation is presented. Its derivation is mathematically more complicated than the approximation just described, but in the end both approximations are very similar. Variable values at auxiliary points can be computed from variable values and gradients at cell centers as described in slide 14. The approximation of the derivative is then given by this expression. The blue framed part is treated implicitly, that is, it contributes to the matrix coefficients in the algebraic equations for the two neighbor cells. The red framed part is treated explicitly as a deferred correction, that is, computed using values from previous iteration. On uniform Cartesian grids, the above approximation reduces to the standard central difference. The red framed part becomes zero when auxiliary points collapse with cell centers. Several approximations presented so far rely on using gradient vectors from cell centers. Let us see how gradient vectors can be conveniently determined on polyhedral grids. One way of computing gradients at cell center is based on Gauss theorem, which states that the volume integral of the divergence of a vector, here phi I, is equal to the flux of that vector through the volume boundary. The dot product of a Cartesian unit vector I and phase surface vector is equal to the surface vector component Si, and using midpoint rule approximation, the surface integral is approximated as the sum of products of phase values of the variable times surface vector components in the direction I. By applying midpoint rule approximation to volume integral, we obtain the ith gradient vector component by dividing the approximation of the surface integral with cell volume, as shown in this expression. Another option is to use shape functions, for example linear. The difference between variable values at the neighbor node and at the cell center is approximated as the product of the gradient vector at cell center times distance vector from cell center to the center of the neighbor cell. We can write such expressions for centroids of all neighbor cells. The unknowns in these expressions are the three components of the gradient vector. Because we have 4 for a tetrahedral cell or more such expressions, the number of neighbor cells for polyhedral grid is around 10 to 15, and only 3 unknowns, we must use least squares approach to determine the 3 components of the gradient vector. Irrespective of grid type, we often have to deal with non-conformal grid interfaces. For example, when one grid block slides along another one, like between a rotor and the stator of a turbo machine. One option at such interfaces is a non-conservative treatment using so-called hanging nodes. Such a situation is depicted in this figure. For the shaded control volume around node P, the ghost node E, the hanging node, is placed on the other side of the interface as if the grid from block A was continued across the interface. Thus, control volumes on either side of the interface retain their topology and assume the existence of a neighbor on the other side of the interface. Variable values at the hanging node E are computed by interpolation from cells on the other side of the interface. One possibility is to identify the nearest cell center in the grid from block B and then compute the variable value at location E using the variable value and the gradient at the neighbor node NE as shown in this expression. The sums of fluxes through interface faces on one block A and on the other side, block B, will normally not come out equal. In most cases this is not a problem because the inequality is a consequence of discretization errors from interpolation. These errors tend to zero as the grid is refined and are not larger than the errors from computation of convection fluxes at regular cell faces because the distance over which is interpolated is never greater than half a cell width. If desired, one can apply a correction procedure to ensure global conservation. One sums all interface fluxes from both sides and computes their ratio. The fluxes on one side of the interface are then scaled by the computed ratio, which makes the sums from both sides equal. This approach is often used with block-structured grids and block interfaces, and especially for sliding grids. Another option at non-conformal grid interfaces is a conservative treatment, using mapping of faces from both sides onto interface. Control volumes on either side of the interface change their topology. The faces lying in the interface are used only for mapping, not for computing fluxes. New faces are identified as pieces of interface common to two cells. The list of such faces has the same ingredients as the list of regular faces separating two cells. These faces are treated as regular internal cell faces, so the CFD part of the code does not need any amendment. However, one needs to write a separate piece of code which does the mapping of original faces onto interface and creates the new faces. This is tricky for complex 3D geometries. In 2D, this is easy, as can be seen in this figure. Pieces of interface line, which are common to two cells, can be uniquely defined. In 3D and on curved surfaces, it is non-trivial to identify each piece of interface common to two cells. The curvature, relative phase position, and tolerances play a role. If the grids on either side of interface are moving relative to each other, like in sliding interface, the mapping needs to be repeated in each time step, and the list of faces must be updated. This approach is used when cells are treated as polyhedra anyway. Midpoint rule is also the simplest second-order approximation of volume integrals that is applicable to any polyhedral control volume when node P is at the CV centroid. For example, for source terms, we simply multiply the specific source at node P by the cell volume. No interpolation is necessary because variable values and fluid properties are stored at the cell center. However, some source terms do require gradients to be computed at cell centroid, especially those for turbulence models, as will be described in lecture 32. Pressure terms in momentum equations can be approximated in two ways, using a conservative or a non-conservative approach. In the former, pressure forces at cell faces are computed in the same way as convection fluxes. In the latter, pressure gradient is treated as the volumetric force and is integrated over cell volume. Note that if the gradient is approximated using Gauss theorem, the two approaches become equivalent. See slide 17. This completes the description of discretization approaches for various terms in conservation equations that need to be approximated. Momentum equations have a slightly more complicated diffusion flux than the generic scalar variable. See slides 6 and 7 of lecture 16. However, the extra terms can be approximated using the approaches described for the generic variable. The next important step when developing a method for solving the Navier-Stokes equations for an incompressible flow is the derivation of a pressure correction equation. In lecture 17, the implicit fractional step method was described, and in lecture 18, the simple algorithm and related variants were presented. Here we concentrate on features of simple algorithm specific to arbitrary polyhedral control volumes as opposed to Cartesian grids treated in lecture 17 and 18. The discretized momentum equations have the following form. See slide 20 of lecture 18. The central coefficient AP, that is the coefficient on the main diagonal of the coefficient matrix, times the velocity at cell center, plus coefficients multiplying velocities at immediate neighbor cell center, sharing the phase k, with the cell around node P, equals the source term QIP. The source term QIP contains body forces and all terms treated as known, for example, all deferred corrections. It also contains the discretized pressure gradient term. Irrespective of how this term is approximated, one can write the pressure contribution as an approximation of the gradient at cell center times cell volume. If the pressure term is approximated in a conservative way as a sum of surface forces, the mean pressure gradient over this cell can be expressed as follows, as described in preceding slide. Following the approach described in section 821 of the book and slides 22 to 25 of lecture 18, The interpolated cell phase velocity is corrected by subtracting the difference between the pressure gradient computed at cell phase and the interpolated gradient. Only the normal velocity component contributes to the mass flux through cell phases. It depends on the pressure gradient in the normal direction. Therefore, by analogy, the following expression for the normal velocity component Vn equal scalar product of velocity vector v and unit vector n at the cell phase can be written, although we do not solve an equation for this component. The coefficient on the main diagonal is usually the same for all three Cartesian components, so we can assume that it would be the same if the coordinate system was rotated so that x corresponds to n. From pressure gradient at the cell centers, one can compute the interpolated gradient in the normal direction. What remains is an approximation for the pressure derivative in the direction normal to cell phase at its center. To this end, we can apply the same approach described in slides 15 and 16 for diffusion fluxes. The pressure derivative with respect to n can be approximated by a central difference using auxiliary points on the phase normal as follows: the value at this point minus the value at this point divided by distance. The values of pressure at the two auxiliary nodes can be calculated using cell center values and gradients, as given by these expressions. This leads to the following expression for pressure derivative with respect to n. Because pressure correction tends to zero at convergence, it is usually sufficient to keep only the first term on the right-hand side. The red framed part can be neglected. The simplification just mentioned leads to the following expression from which the velocity component normal to cell phase is computed. The correction term in square brackets represents the difference between pressures at the two cell centers and the approximation to it calculated using interpolated pressure gradient. When the pressure distribution is smooth, this correction term is small and it tends to zero as the grid is refined. As shown in slide 23 of lecture 18, the correction term is proportional to the product of grid spacing squared and the third derivative of pressure at the cell phase, and thus represents a second-order approximation. The pressure gradient at the cell center is available as it was calculated for use in the momentum equations. The mass fluxes calculated using the interpolated velocity are denoted by asterisks. They do not in general satisfy the continuity requirement, so their sum over all phases of the control volume results in a mass imbalance. The cell phase velocities must be corrected so that mass conservation is satisfied in each control volume. Following the method described in slides 22 to 25 of lecture 18, we correct the mass fluxes by expressing the velocity correction through the gradient of pressure correction. By introducing the approximation for pressure derivative along phase normal from slide 23, we obtain the following expression for mass flux correction at phase k. On a good quality grid, the framed part is small relative to the leading term. Because it complicates the derivation of a pressure correction equation, and at convergence all pressure corrections are zero, it is usually neglected. By summing mass flux corrections for all cell phases and mass fluxes from the predictor step, we obtained a corrected continuity equation. This leads to an algebraic pressure correction equation for each cell. See slide 24 of lecture 18. Neglection of the framed part requires strong under-relaxation of pressure when the grid is highly non-orthogonal, with alpha p equal 0.1 or even less. For incompressible flows, the coefficient matrix of the pressure correction equation is symmetric, which allows for the use of specialized solvers for symmetric matrices, like incomplete Cholesky preconditioned conjugate gradient solver, ICCG. The mass fluxes through cell phases, cell center velocities, and pressure are corrected as shown by these expressions. The grid non-orthogonality can be taken into account in the pressure correction equation iteratively, that is, by using the predicto-correcto approach. One solves first the equation for p prime in which the frame path in slide 26 is neglected. In the second step, one corrects the error made in the first step by adding another correction and the neglected path of the first correction, and so on. See section 9.8 of the book for details. Let us summarize this lecture. Because the midpoint rule approximation of surface and volume integrals does not depend on the shape of polygonal surfaces and polyhedral control volumes, it is easy to derive finite volume methods based on second-order approximations for polyhedral grids. A suitable way of deriving an approximation of convection and diffusion fluxes is based on auxiliary points on phased normal and deferred correction approach. Variable values at auxiliary points can be conveniently computed from values and gradients at cell centers. Gradients at cell centers can be conveniently approximated using Gauss theorem or linear shape functions and least square method. For the computation of mass fluxes through cell faces, velocities from cell centers are interpolated and the Rien-Chow correction is applied in the same way as for Cartesian grids. A pressure correction equation is easily derived by neglecting grid non-orthogonality, which is justifiable because at convergence pressure correction tends to zero.